I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
Okay, so I'm very excited about this episode today, Jam. I'm always excited about them. But I'm extra excited.
What else is new?
Well, I learned a new thing from a chemist coworker, so that's part of why I'm so excited.
Oh, nice. Okay, cool. New things are cool.
Yeah, new things are cool. So shout out to Dr. Corrales for bringing this up in their class. Dr. Corrales teaches the OChem class that I TA for this semester because I opted not to teach my own class because I'm trying to graduate.
Right.
And so I get to sit and learn from Dr. Corrales twice a week along with their students. And I was so excited when they shared this tidbit of information.
Nice. I'm very interested. I'm intrigued.
So Dr. Corrales learned from an article from Chemistry and Engineering News that blue jeans, like denim that's visually blue to our eyes, is actually dyed yellow, not blue.
Okay.
Okay. There's so much chemistry behind it.
So I don't know about that. I'm thinking... Could you ask Dr. Corrales, like, are you sure?
I did one better, and I looked at Dr. Corrales' resources, and they are sure. So don't worry.
Okay.
So they're dyed yellow, but then they turn blue quickly when they're exposed to the air.
Interesting. Okay.
So you get 3 chemistry lessons, and actually I think you've learned some about all of these chemistry lessons before, but you'll get to revisit 3 chemistry lessons that tie into what happens here.
Okay, interesting.
And then I have a little analogy that I came up with, but I'm hoping you can come up with a better one.
Or a dumber one, whichever adjective is more.
No, definitely a better one. I think you'll be able to do a better one.
Okay, I'll try my best.
Lesson number 1 is like dissolves like. So similar things interact with similar things molecularly.
Okay. Definitely remember you saying that for sure. Like,
yes.
Multiple times.
And your teacher said that too.
Probably so.
In your high school chemistry class.
Yeah.
And then 2, color comes from the way molecules absorb energy, and that is dependent on the way those molecules are structured. Okay, and then 3, oxidation and reduction in chemistry is all about increasing bonds to oxygen or decreasing bonds to oxygen.
Okay.
It's a little bit more complicated than that, but that's a simple enough definition for this conversation.
Okay.
So those are the 3 main lessons. So that's an overview of what you're going to learn. So now let's go kind of in depth on each one.
Okay.
So 1, like dissolves like. This has to do with the polarity of your molecule, right? So we've talked about this all the way back in like the second episode where we talked about geckos on walls. Some molecules are polar and some molecules are nonpolar. And when we talk about polarity in chemistry, it's all about the distribution of electrons. So if you have a concentration of electrons in one area of your molecule, there's going to be a partial negative there because electrons are negative. And the absence of electrons on the other side will give you a partial positive.
Right. And we talked about this even back at the first episode with like water and soap and grease and fat and all that stuff. Yeah. Okay.
Oh, yeah, you're right. We talked about that in the very first episode. So you can go back and listen to those if you want slightly more in depth. But just as a brief overview, so there are molecules that are polar and molecules that are nonpolar. Molecules where the electrons are evenly distributed and molecules where the electrons are not quite evenly distributed. And so there's partial positive and negative or poles. And you've seen this in your everyday life because everyone has seen oil and water not mixed together.
Right.
And if you haven't, go into your kitchen and get a bowl of oil or a bowl of water and pour the other one on top. So oil likes oil, water likes water, but oil doesn't like water because oil is nonpolar and water is polar.
Got it.
So that's lesson 1.
Okay.
Lesson 2 is color comes from the way that molecules absorb energy, specifically light energy.
Mm-hmm.
And you're actually going to get to go in depth on this upcoming week when we rebroadcast the episode on bleach and how bleach works.
Nice.
So I'll give you a quick overview of that, but it'll be better if you go listen to that episode.
Got it.
So the way that molecules are structured allows them to absorb different amounts of energy. And just because it so happens that molecules that have a lot of alternating double bonds tend to absorb energy in the visible region of light, which means we can see the light that they reflect back as color.
Right.
So typically, things that are highly colored, like reds, greens, blues, even some of yellows, have a lot of alternating double bonds.
Mm-hmm.
So that's something to note. But it also is important to note that the way those alternating double bonds distribute electrons means that they are usually also not polar.
Okay.
Okay, so that's lesson 2, is that color comes from the way molecules absorb energy. That's dependent on the way the molecules are structured.
Mm-hmm.
And the way that they're structured also means that they're usually not polar.
Got it.
Due to these alternating double bonds, they kind of create a highway where the electrons can be shared really evenly.
Got it. Yeah, so they're not concentrated in one sort of side of a molecule more than another. They move about freely.
Right. And that characteristic also means that they tend to absorb light in this region that's visible to us.
Got it. Okay, cool.
Okay, now your third lesson is about oxidation and reduction in organic chemistry.
Okay.
We've talked about redox reactions in 2 settings. We've talked about them when you think of like rust and how oxidation and reduction occur in metals.
Mm-hmm.
But we also talked about that in terms of making more or fewer bonds to oxygen.
Okay.
I tend to think of it as an organic chemist. I think of oxidation and reduction less as just how the electrons are exchanged, which is more the rust type of way of thinking about it. And instead, I think about, are we increasing bonds to oxygen or decreasing bonds to oxygen? So, or, there's a broader definition, more electronegative atoms get more bonds, that's oxidation, but that's more complicated than you need to know for this episode.
Okay.
So oftentimes we'll see this in organic chemistry as a group like alcohol, which has one bond between carbon and oxygen, being oxidized to something called a ketone, which has a double bond between carbon and oxygen.
Okay.
There are those double bonds between carbon and oxygen present in indigo dye that goes on jeans.
Okay.
Okay. But if you wanted to reduce it, you would take it from the double bond between the carbon and oxygen to a single bond between carbon and oxygen known as an alcohol.
Okay.
Okay. So those are your 3 lessons.
Okay.
1 is like dissolves like, so polar likes nonpolar. 2 is color comes from the way molecules absorb energy. That has to do with their structure. And usually because of their color and their structure, they're also nonpolar.
Right.
And 3, you can oxidize and reduce molecules by adding more bonds to oxygen or taking away bonds to oxygen. And there are carbons with 2 bonds to oxygen present in our indigo dye. Okay. So now I'm going to tell you how all 3 of these come together.
Okay, sweet. I'm very curious.
Okay. So indigo dye is nonpolar because of its structure and the way its electrons all share these nice alternating double bonds.
Okay.
So it won't dissolve in water, which means you can't easily dye your jeans in it.
Okay, I see.
So we use a reducing agent, which reduces those carbon double bond to oxygens present in indigo dye down to an alcohol.
Okay.
Which interrupts the highway of double bonds, these alternating double bonds that let all the electrons spread evenly. It interrupts that flow.
Okay.
And creates some more polar sites in the molecule.
Okay.
You can make that even more polar by putting it in a basic environment, but that's a different lesson for a different day.
Okay.
I just want people who know chemistry a little bit more to know that you also can put these indigo dyes in a basic environment and it will deprotonate the alcohol. But if that didn't make sense to you, just focus on the fact that we can use a molecule to do a chemical reaction to reduce our double bonds to oxygen to single bonds to oxygen,
Okay.
which interrupts the flow of electrons, creating polar sites in our molecule.
Okay.
And that means that it can interact with water now,
Okay. Which is what we want.
which is what we want. But it also means that we've changed the structure of the molecule itself. So it is actually now a different molecule that is no longer blue, but yellow.
We messed with stuff that affects the way it takes in energy or distributes in the region of visible light, and so it stops looking the same.
Exactly.
Wow.
We've changed the way that it absorbs energy by changing bonds. So now it doesn't look the same to us.
Okay, that's weird.
So it turns yellow and it's now in the water in this basic watery environment. And then you dye your jeans that color so it's yellow.
Okay.
And then you take it out and it gets exposed to air, which has oxygen in it, which is an oxidizing agent. So the molecules, the dye molecules, then become oxidized again. They return back to their original state, which is a nice indigo color.
Interesting. Huh.
And that is how your jeans get dyed yellow to become blue jeans.
Wow. So, and that's true across the board. Like most, like blue jean dyeing in manufacturing places, have a stage where they're yellow for a bit.
I think so. That's what I only could find 2 resources on this. They're both from the American Chemical Society. So I think industry secrets, sometimes kind of keep it close to their chest. But they said that 95% of synthetic indigo dye that will need to be reduced in order to be dissolved in water is that yellow color.
Okay.
It should be that reduced state that then is oxidized after it's on
Wow,
your
man,
jeans.
that's weird. That is so interesting. It's like you're trying to solve one problem, which is just like, we got to get this dye in the water so we can actually have a big vat of it or whatever so that we can dye these jeans. But like the solution to it also changes the color. Like obviously they're not trying to change the color. That's not their goal.
Right.
But when you're messing with stuff under the hood, sometimes it has consequences like that where it changes the color temporarily.
Yes.
That's crazy, dude. That's so strange.
It also really informs this, the function of the molecule and the way we perceive the molecule has everything to do with the bonds and the way it's structured.
Yeah.
Which, as a chemist, I think about that all the time. So when I saw this, I was like, that wouldn't be a big deal for me to think about, but I bet that's crazy for other people to think about.
And in our other episodes where we've talked about color and, energy being absorbed and all that stuff and things being like in the visible range of light and all that stuff, there have been a couple times in those episodes where I've kind of gotten a little tripped out by being like, but so it's just how we see it and the waves, the frequency of all that. It's just, man, it's very trippy quickly, especially for people like me who don't think about it all the time,
Well, even for me, it's hard. There are times I'm trying to explain color and I get a little bit too far in it. And I'm like, does any of this make sense? Why is the world the way it is?
Yeah, that's funny.
So I tried to come up with an analogy to help us think about this. And I think because I just watched Encanto, the only thing I could come up with was Mulan. So Mulan wanted to go fight in the army, right? But she didn't fit in with the army.
Right.
So she changed herself. She changed the structure of her attitude and her appearance and everything to fit in with the boys in the army.
Right.
But after she became accepted there, slowly she did sort of start to revert to her natural state.
Right.
And it was a little bit more jarring, right? Because she got kicked out of the army eventually when they discovered or whatever. But that is how I think of the dye. We change it so it fits in. And once it's there and it's infiltrated the water, it gets stuck to, it bonds, really is actually, I think, what happens. That's a whole other episode. To your denim, and it's there in its undercover form. But as the light hits it, it becomes exposed for what it really is, which is indigo dye.
Right.
It's not just exposed, it's physically changed and then changed back. But that was the best thing I could come up with. But I thought maybe you could come up with a better.
No, that's good. I get it. I get it. And that really makes sense. And what's fine in the case of the dye, the indigo dye, is that it's already done the job it needs to do. And Mulan hadn't quite gotten that far yet, I guess. But
that's true.
But it's kind of cool that in the case of dyeing denim, it's like, oh, it's already gotten in there. It's become a part of the jeans. It has changed the color of the jeans. Denim's made out of cotton, so it's probably some very light color originally. And so it's already done that. It's integrated itself in. And then it's okay if it changes it back because guess what? Mission accomplished.
Mission accomplished. It's changed the color of the denim forever, and now it can oxidize to become the blue color we want it to be.
That analogy helps. And the only thing I can think of that comes to mind for me is something that's just very similar. It's not like a hugely different way of understanding, but just like the classic, Trojan horse myth sort of deal is just hiding inside of something else like that. Like, oh, hey, here's just a big old wooden horse. Nothing to see here. It's like, okay, cool. Come on in then. In that case, let's just bring this wooden horse inside of our castle. And then once they're in, then they go right back, come out of it and our soldiers and do what they came to do or whatever. That's probably not a perfect analogy in that case because they're literally hiding inside of something else, which at the molecular level is not what's happening. It's not like it's disguising itself inside of like some sort of larger molecule or whatever. But
yeah, that's more of like what happened with when we talked about air fresheners how they take in the odorous molecule. Yeah, because it's literally changing.
Yeah.
And then changing back.
Yeah.
It's undergoing a chemical reaction to turn yellow, doing the deal, and then undergoing a chemical reaction back. But just like rust, that's what it wants to do. It's more stable in the oxidized form. So once it's blue again, it'll stay blue.
Yeah. That makes sense. Yeah, I don't know if I can come up with a better analogy. Like that one really works.
Well, then do you want to just try to explain those three major concepts back?
Yes. So the first concept is like dissolves like. And that's basically the beginning of this whole thing as well, because at the start, the indigo dye and the water are not like.
Exactly.
They're like not even like at that point. You know what I mean? And so
I know exactly what you mean.
Yeah. And so we have to try to figure out how to make them like, and to be more specific for anyone who's like annoyed and wants us to use real words, the indigo dye is nonpolar at the start, correct?
Yes, it's nonpolar like oil.
Like oil. And the water is like water, which is polar. And,
exactly.
And so they, at the moment, cannot mix, but that is essential to end up to dye these blue jeans. So then the chemists scheming and plotting and trying to figure out a way to solve this problem were like, okay, is there a way we could make the indigo dye to be polar for a little bit temporarily so it could integrate with the water and become a big old vat of blueness for us to throw these pants into. And so then the second one has to do with the interesting and very complex topic of just how light even works and how we even see it and perceive it, which has everything to do with the bonds of whatever object we're talking about, especially in the case of having a really good way for electrons to move throughout and absorb energy well. And what's the word then? Like reflect or
Yeah,
sort
so
of-
the light, a certain amount of light is absorbed and anything else is reflected back. So that's where we see the color.
yes.
So, and these alternating double bonds that have an even distribution of electrons, they're very stable. And so it takes a specific amount of light for those electrons to go to the excited state. That's where they absorb energy. So that whole thing is kind of complicated. But they absorb an amount and reflect the rest back.
Yes. And so in the case of the indigo dye, it has a lot of alternating double bonds to start.
Mm-hmm.
And it is absorbing light and then reflecting this very strong blue. The wavelength of what it's reflecting is this very deep blue color.
Mm-hmm.
And so it's all, what we see is all tied up in also the molecular side of it, which is also tied into the fact that it is nonpolar. It is,
right.
That's why it's blue.
Mm-hmm.
And so the problem there is that, okay, we want to integrate this with the water, but not only does it not want to integrate with the water because it's nonpolar, but also the reason it's blue is because it's nonpolar. The color and all that stuff is all connected. And so
the form, the color, the structure, the ability to interact with other molecules, those are all tied intricately together.
And so then the third concept where they have to start these, hypothetical, I mean, they're real, but I don't know who they are, chemists who are coming up with this stuff somewhere.
Yeah, I don't know who came up with this stuff.
We're like, let's mess with the bonds to oxygen and mess with the polarity, the non-polarity of this indigo dye.
Mm-hmm.
And that's where we get into concept number 3, which is that if we increase or decrease the bonds to oxygen atoms, we can reduce, or what's the opposite of reduce?
Oxidize.
Okay. Reduce or oxidize something.
Mm-hmm.
And so what they do, I might be forgetting this. What did they introduce to?
It's known as a reducing agent.
Okay.
So it's just something that's good at breaking the bonds between carbons and oxygens and adding in hydrogens instead.
Okay. That part either you.
So it's usually something with a lot of hydrogens.
Okay. So they introduce something that is really good at that. A little secret agent, a reducing agent. And
yeah.
And so all these really good bonds to oxygen that are happening get disrupted, broken or redirected or whatever, because they've introduced something that takes a lot of them or breaks a lot of them or
yeah, it just will break them.
Okay.
So if there's a carbon with 2 bonds to oxygen, it turns it to a carbon with 1 bond to oxygen.
Got it.
So it reduces the number of bonds to that oxygen by just adding hydrogens in instead.
Got it.
It's similar to the hydrogenation reaction we talked about way, way back in like episode 4.
Okay. Got it. So as it's happening, imagine, if you can, at this like way zoomed in level, this reducing agent is added. And so the bonds to oxygen start going from double to single. And this highway that allows the electrons to move about and be distributed very well slowly starts getting disrupted and changed. And now there's all these single bonds. And so slowly, if we could, sort of watch it or something, it may happen all at once. Who knows?
If you could slow down and watch it at a molecular level, if you could shrink yourself down and slow down time.
Then it's also
my dream, by the way, is to shrink down to the molecular level and watch it all happen. That's my dream.
That'd be awesome. Very Miss Frizzle.
Oh my gosh, yes, that is it. I want to be Miss Frizzle on the Magic School Bus and go down to the molecular level.
And then because we're starting to mess with stuff that affects how it absorbs energy, how it absorbs light, reflects light and stuff, this indigo dye stops being blue and starts being yellow.
That's right. That's right.
But then it also has become polar. It has like polar sites, as you said. It's not this non-polar dye we once knew. And now it can be mixed with water and we can create these large vats to dye all of our pants and stuff.
Yeah.
But it seems for a bit that we were dyeing them yellow because...
Yeah, you are dyeing them yellow. What the heck? We're trying to get these blue.
And I guess baked into this, you kind of said this earlier, but basically they would have to be, at the moment, not exposed to a lot of oxygen while they're being dyed, correct?
Well, I think because usually it's a solution with the oxidizing agent and it's in a basic environment and the water is there. So I don't think it can be reduced back in the situation.
Okay.
Like the things that make it go yellow are still there in the solution. Yeah. So I think they probably take it out, rinse all that stuff off, and then it gets exposed to the oxygen and in an environment where that does some damage.
Okay, got it. So these pants are dyed yellow, and then once we remove them from the situation, we've already done what we needed to. We got the dye in the water, then we got the pants in the water and the dye. We got the dye in the pants. Got the pants. Now we can get the pants out of all that mess that we've just done and get all the chemical stuff off, all the extra dye, all the base, all the reducing agent stuff off the pants. And then the double bonds to oxygen start to be able to come back together.
Yes, because oxygen in the air is an oxidizing agent.
Yeah, which makes sense. Wording wise, it seems like oxygen should be an oxidizing agent. And if not, then somebody messed up when they were naming stuff.
Yeah. Well, people mess up in a lot of ways in naming, but this one is one that makes sense.
Cool. And then finally, our blue jeans are blue.
Yep.
And all is right in the world once again.
That's it. You did it. Good job.
That's kind of tough. I mean, there being so many lessons, obviously a lot of our episodes have multiple chemistry things at play because that's just how real life is. But this having 3 things, especially some of the hard ones that is like, bonds and light and energy and stuff, it's kind of trippy.
It is. You have to have a good foundational knowledge to understand why this happens. So for organic chemistry students who have been they're organic chemistry 2 students, so they've been in 3 semesters of college level chemistry, we could show them that and they understood what was happening very quickly. But then I was thinking about boiling it down and I realized that we were going to have to go more in depth. But I thought it was worth it. And I think it's a fun episode. Yeah,
that's definitely cool. Definitely fun and challenging. So I think there could be some folks, if this is your first episode you've ever listened to, it might feel like, man, are they all this hard? And it's like, definitely not.
Definitely not.
And if you're somebody who knows, like Melissa was just saying, who knows a lot of organic chemistry already, you might be like, this is easy. It's cakewalk. But
I don't know. I still think it's hard. Even after doing organic chemistry for 10 years, it's still difficult for me to think through all of the aspects of color and how changing just like a few bonds can totally change the color of a molecule and what that does to the energy that absorbs and reflects that. Yeah, that can still confuse even someone who's been doing it a long time.
Yeah.
So.
Okay, cool.
So I don't think anyone will think it's a cakewalk per se.
Yeah.
All right, great. Well, I thought that was really fun. I don't have any fun facts for you this week. That was my whole fun fact for you. But I am wondering if you had anything fun happen to you, because I feel like I haven't seen you lately.
Yeah.
So what's going on in your life?
Yeah, I had a somewhat fun thing that you may have your own version of too, but last week, many people across the U.S. were in a similar situation where we had varying amounts of snow hit like basically almost half the U.S. all at once, which is kind of nuts. But it was kind of cool because my son, last time this happened a year ago, was only about 7 months old or so. And was able to recognize that snow is different and be kind of like, this is interesting and stuff. But this time around, of course, way more interested, way more able to like actually enjoy the snow than he was last time.
Mm-hmm.
And so that was a lot of fun. So we went out and kind of stomped around in the snow with him on the 2 days of snow we had, and just got to watch him be fascinated by it and be interested in the fact that it like makes footprints and everything looks really different. And it's kind of fun, especially the second day when it kind of refreezes a little bit, how like when you step, it kind of like crunches in a little bit more, you know, it's like just more of a crispy kind of crunchy snow out there. And it was a lot of fun. We had to kind of improvise a little bit to get good going out and playing in the snow clothes on him. We just didn't really have that. We hadn't needed it so far much. I mean, in Texas, the times it snows are so few that the idea of being like, let me get some really good snow clothes for my like 1-year-old or whatever.
Who's not going to be this size again in like 2 weeks.
Exactly. Yeah. Every time it snows, he's not going to be the same size he was last time we had stuff. So, and how can we ever know? Like, how can we predict what, like, when it's going to snow? What size is it going to be? So anyway, but it was a lot of fun. We improvised and went out and stomped around and it's just cool, you know, to see him experience something that he has not experienced and like watch him be curious and all that stuff. Anyway. So. And
I saw some of those pictures of him staring out the window and pointing at the snow, and it was really cute.
Yeah, while it was still falling, he kept doing that, almost like he thought like we hadn't really seen it, or like I guess the fact that we weren't like mind blown by it was kind of confusing him, and so he was like, "Guys, look out there! There's stuff falling from the sky and it's getting everywhere."
Yeah, it was pretty cute.
Yeah.
I felt similarly. I was very excited about the snow day, but actually what I'm going to talk about is not my version of that.
Okay.
Mine is actually kind of like more of a bummer. But I feel like it's good to share all parts of our lives. And mostly we focus on the fun stuff, but
yeah,
I want people to know, you know, some of what it really feels like to be a chemist day in, day out.
Yeah.
So I've been working on my PhD for 7 years, and here we are.
Uh-huh.
We're at the end. Maybe it's 6 years. I don't know. I lose track. I think maybe it's 6. I started in 2015. It's 2022.
Yeah.
We're nearing the 7-year mark, and I'm supposed to graduate at the end of this semester. I have a deadline to where I need to turn in my dissertation, but that requires a lot of writing.
Mm-hmm.
And it's just been really hard lately. It's been hard to get the motivation to do it. It's scary to come up on the end of doing something that you've been working on for so long.
Yeah.
Like, what am I going to do next? I mean, I have a lot of ideas and I'm excited about what may happen next, but it's also just a really big change.
Yeah.
And so the mental work of getting progress made is difficult. And I'm really thankful because I have a really good team supporting me. I have an incredible boss. I have 2 incredible bosses. I have, a great husband, great friends, great family, but it has just been a little hard lately to work on that.
Yeah.
And it's been really consuming my brain. So that's the biggest thing that's been going on for me lately.
Dang, man, that's tough. But I get it. I mean, I get what you're saying. It's like, it's good to give a realistic picture. And my guess would be, I would be surprised if most people working at their PhD in all kinds of fields would not be like, I totally felt exactly that way multiple times.
Yeah.
So,
I'm sure.
That's got to be normal.
And I've been lucky with this one. There hasn't been as much pressure to get stuff done in a certain amount of time. That's just not how my team now really functions,
Yeah.
But there's a deadline that's imposed outside of all of us, so that pressure being there. But I do think it's really normal, and I have great people to help me cope with it, and I'm really thankful to all of them. But I just wanted to share that really is what's been going on in my mind most of the time lately.
Yeah.
And I just wanted to, tell our listeners that's kind of what's happening. So, but this part of it stays fun and refreshing, and it is always nice to hear from our listeners. We got that really nice message from Emily C. a few weeks ago, and I it's like, oh, this is why I'm doing it. It helps me stay encouraged and excited about finishing up and getting to focus more on science communication.
Yeah.
So,
Yeah, absolutely.
So that's it. That's what's going on with me.
Sweet. I mean, it's so weird because I'm like, I'm so used to the like language that's normally in my head is like, cool, that was fun, or that sounds fun, or like.
Yeah, I just was like, actually, it is terrible.
Yeah.
No, it's not terrible. It still is very exciting news that I'm this close.
Yeah,
like I'm in
yeah.
the final stretch, and this is really normal for the final stretch. So it's both exciting and annoying.
Yeah. That makes sense.
But also, I do want to shout out one more time Dr. Corrales for one, being one of those amazing support systems in my life, but also two, coming up with this episode idea. This was such a good idea, and I'm really thankful for that.
Yeah, definitely. And if you out there, listener, have an idea or a question or something you've heard about or something you've always just kind of wondered about that could be chemistry, please let us know. We'd love to hear your ideas or your questions. So you can share those with us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/Chem4Your-Life or click the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app or rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jerem Robinson. References for this episode can be found in our show notes or on our website. Jerem Robinson is our producer, and we'd like to give a special thanks to A. Collini and S. Navarro, who reviewed this episode.